Hello and welcome to our awesome Introduction to Computational Physics course, Physics 352 at Northwestern. I am your instructor, Sasha Chikavskoy, and today we're going to take a deeper dive into the guts of C, including pointers and functions. Let's get started. But before we get there, let us cover a few preliminaries. The first assignment 1, has been posted on Canvas. It actually has been there for a while, but because the assignment is due a week from now, it's a good time to take a look at it and start working on it. It's due 1 minute before midnight a week from now on Tuesday, January the 26th. How do you submit the assignment? You submit it through the Canvas website of the course. You submit all of the information that is necessary for Lindsay and I to compile and run your code. So, for instance, if your code contains the C files, which it should of course contain, and the header files, then you submit both the C and the header files using this notation. For instance, if you're submitting solutions to assignment 1, problem 2, then you will name the C source code assignment 1_2.c. So X here is the number of the problem for whom you're making the submission. All the input files, if they're necessary and not provided with the problem, please submit them as well, just as the output files, if this is what the problem asks you to submit. Please submit the code output log, that is whatever the code prints out into the terminal. You can copy and paste that into a file that you can name assignment 1_2_log.txt. In this example, I'm using problem 2 submission. If a problem is asking you for text responses or plots, please combine all the responses and plots into a single PDF file. For instance, name it assignment1.pdf, where you would start with your response and plots for problem 1, continue to problem 2, and so on. And if there is no response, then you can skip that problem for which there is no response needed. Finally, there is no need to submit the executable because executables are machine specific, and Lindsay and I are going to be compiling the code that you provide us. So hopefully that is clear. If you have any questions, please, as always, reach out to Lindsay and I. Well, what are we going to be talking about today? We're going to go into a little bit of more details of what we covered in the previous couple of lectures, and then we're going to get into functions and pointers with arrays. So before we get any further, there is a really important topic that we need to get out of the way, and that is operator precedence. It's really important in order to be able to understand math notation in the code. For instance, what is 2 plus 2 times 2? Well, because multiplication takes precedence over addition, it is 6, not 8. And so precedence of operators is really important to understand expressions like these. Does plus plus x times y mean plus plus x first and then times y? Or do you attempt to operate plus plus x on the product of x plus y? And what would that even mean? So in order to create the rules that govern precedence, C orders operations by precedence level. There are a bunch of different levels, and within the same level, the operator precedence is done by the associativity, that is left to right or right to left. So let's take a look at the table that lists that. So here is a table that lists the operator precedence level, the operator itself, and the description of the operator. Here is the associativity of that operator. So for instance, if we take operator precedence level 1 group of operators such as I++ or I-, that is a suffix, increment, or decrement, these are operating under the left to right associativity. So the operators within this group are going to be executed starting with the left and continuing to in the right direction, and so on and so forth. This is the high precedence level that is below lower precedence level. And you can see that there is, in group 2, there is a prefix, increment, and decrement. So for instance, plus I and minus I will be here. The sign change, minus I will be here. In precedence level 3, there are multiplication and division. Plus and minus, addition and subtraction is in group 4. As expected, the precedence level is lower of multiplication and division than, is lower of the addition and subtraction than of the multiplication and division, and so on and so forth, ending up with the direct assignment and so on. So let's take a look at how this works in practice. Here is an example that might look mind-boggling first because there is a potpourri here of various operators. But what this actually means is b plus equal 5 takes precedence over the multiplication. And then this combination of minuses and pluses actually means increment a by 1 first, change the sign of a, and then multiply it by the value of b plus 5. While changing the value of b as well. So the end result will be 3 plus 5, or 8, times minus 1. And so that will be 8 times 1, or simply 8. So let's talk a little bit more about these plus and minus, increment and decrement operators. There are two flavors of these operators. There is a prefix and suffix flavors. Prefix means just like in plus I, please modify the value and return it right now. Suffix means please modify but return the original value before it was modified. But the subsequent statements following that one will see the modified value. Let's take a look at how it works in an example. So let's take a look at this code where we start with the value of foo equals to 1. And then we're going to print out plus foo. Because plus is a prefix increment, what will happen is that value of foo will be updated by 1. It will be incremented by 1 in place. So the value will be incremented to 2, after which it will be printed out. That's why we see 2 as a result. Just to be sure, we're going to print the value of foo once again, and of course, it's still unchanged. It's still 2. Then we're going to decrement the value of foo, but using a postfix decrement, which means that the original value of foo will be printed out, 2. After that, the value of foo will be decremented, which we will see in the last printout, which will show us that indeed the value of foo went down by 1. So hopefully this makes clear what the difference between increment and decrement in its postfix and prefix forms are. Another important topic is scope, because various variables can be visible in different places of the code, and sometimes they can be invisible if you are outside of the variable's scope. The most basic distinction is between the global and local scopes. For instance, all the stuff that's declared outside of the main function will have a global scope, and it can be seen, all that stuff can be seen after it's been declared in both inside and outside of main. In contrast, variables that are declared inside of main can only be seen inside of main after the point that they were declared. It's really important when you start using functions, which we'll get to in just a little bit, where global variables actually can be used to share the information between the functions, although this is not a great practice and I strongly discourage you from doing that. But because everybody in science does that until they get burned, well, let's take a look at how it works. Much better way is to create a structure with all the variables that you would like to share between the functions, and every time you make a call to a function that needs those variables, you pass that structure to the function. Then that function modifies the values in that structure, and then you can pass that structure again to a different function, which then will be able to use the updated variables. So that is a much better way of sharing the information between the functions. There is also another related topic to the scope, and that is of shadowing. And shadowing is when you have conflicting definitions of variables in different scopes. So for instance, you can have the same variable foo in the global scope and in the local scope. Outside of main, it's a global scope. Inside of main is a local scope. And the local variable is shadowing the global variable, meaning that once a local variable has been defined or declared, then its value will override the value of the variable from the global scope. So the global scope variable will be kind of covered by the local variable, will be shadowed. So in this case, the local variable foo is shadowing the global variable, and so when you print out the value of foo, you're going to get 22, not 1, inside of main. There is also another layer of complexity that scope can take, and that is if you have multiple nested scopes. You can create as many local scopes as you want by enclosing a chunk of code in curly braces. And you can define new variables inside of those curly braces. And that will be a new local scope. Variables that are innermost to the scope that you're working with will shadow the variables which are outside. So the same applies, of course, to the curly braces and the scopes associated with for, while, and if constructs. Each of them has its local scope. And if you declare, and you can declare variables inside of these constructs, and you can do this independent of whether these variables were already defined elsewhere in main. So you can override the main variables, or you can create new ones. Variables that are declared not at the beginning of main, but somewhere else in the random place of the code can lead to errors. But if you declare them at the beginning of a scope, that will not lead to errors. And we will talk about C extensions and newer standards that actually allow you to relax those strict rules. Here's an example of a nested local variable. Let's take a look over here. We have a global variable foo and a local variable foo within the main scope. So if we print that out, we will see the value of 22, just like we expect. Now we're going to create a local scope between these two curly braces. So now this definition of variable foo equal to 333 will shadow the rest of the previous variables of foo in other scopes. You can see, therefore, when we print it out, we're going to get 333 from this line. If we go down to yet another nested local scope, we're going to see the new value of 444. And once we exit that local scope, we're going to see the ones from the same scope, 333 and 22. Here is another example. This one involves a for loop, where you can see that the local variable in main will shadow the global variable foo declared before main, and the same thing will be true about the bar variable that is declared inside of the for loop scope that will shadow the global variable bar that was declared before main. And you can see this in the printouts over here. The first time we enter this loop, the value of foo is going to be 3. It's not going to be changed at first. And the value of bar will be minus 999 plus foo. So it will be minus 999 plus 3, that will be minus 996. The next time we get into the loop, the variable foo will have been decreased by 1 because of the postfix decrement. And so then foo will be equal to 2, and bar will be equal to minus 997, and so on. And as you can see, the global variable foo will be completely shadowed or overshadowed, you can say, by the local variable foo, and the variable bar that was declared in the innermost scope of the for array will shadow the variable bar that was declared in the global scope. So this is all within the NCC or C90 standard, where you can declare variables only immediately after an open curly brace. but that would be a little bit boring. It would be nice to be able to declare variables wherever you want. And that is what we're going to take a look at when we move from C90 to C99. So look at the same code that we looked before. And what we're going to do is we're going to subtly modify. You actually can define the variable foo right there in the for loop, basically almost anywhere. So we will move this declaration and assignment of foo variable from before the for loop inside of the for loop, just like here. And this foo variable will survive only within the scope of the for loop. So you can see here that in the bar is going to be defined exactly the same way, and you're going to get exactly the same output as before. A very tightly related topic to local scope is that of functions. Once control leaves the local scope, all of the variables that live within that scope will be destroyed. And you can think of a function as that of basically being a local scope, but with extra perks, like an interface for input and an interface for output. So here is a function anatomy that encapsulates that. So function is a scope between these two curly braces which define the function body, and this declaration line of the function contains of the return data type, which could be void if the function returns nothing, function name, and the list of arguments alongside their types. The body of the function consists of statements, just like a scope would, but at the end you can have this optional return statement, return blah, where blah would be the return value of the function, that better be consistent with the return data type that the function declaration lists. So honestly, indeed, the function itself looks like a scope with input and output. But that's not the whole story. Functions can return values, and those could be either one of the basic C types, it could be a void, like I mentioned, that it returns nothing, or it could be a more complicated object. It could be a pointer to a structure, anything you like that you can create a variable for. The arguments of the functions are allow you to pass the information to the function. And keep in mind that all the arguments in C I passed by value. So if you pass a variable to the function and the function modifies that variable inside of itself, then once you leave the function, the original variable that you passed to the function will remain unchanged. In order for the functions to be able to change the variables, you need to pass addresses of those variables to the functions. So this is basically what you are doing here. You can pass by a reference through a pointer instead of passing by a value. You have to declare a function before it is called. Basically, declaration specifies the interface of the function. What is the return value type and what are the arguments and their types. This is kind of a interface manifest of the function. And then the declaration will be followed by definition that describes the guts of the function. What is the function made of? In order to run the function, make a call to the function, the compiler needs to be taught how to call the function to provide that interface. And so if you define your function before main, where you call it from, then you don't need to provide a declaration. The definition of the function has already taught the compiler how to call the function, but it's not always practical to define the functions first, because sometimes functions can call each other. And so it's important to teach the compiler how to call functions by providing declarations or prototype the functions separately from their definitions. Here is an example of how one can do that. So for instance, if we want to call a function, say hello, that prints out hello world, we would have to first prototype it or provide its declaration, declare it. And then once we've done it, then the compiler will know, aha, so function hello doesn't take any arguments and doesn't return anything. So that's pretty easy. So then once it sees say hello, it will know what to do and how to call the function. And so then at the linking stage, it will be able to put together the call and the body of the function. That's why declarations are super important. So again, here is the function prototype. Here is the function invocation or the call to the function. And here is the function definition. That's where the guts of the function are actually sitting. And you can separate the interface and the definition of the function, or declaration and definition of the function, just like we described. But oftentimes they're separated even more so. That allows you to make your code modular. So function is typically written to perform a task that you can, replicate or use in many contexts, can call from many files. And so it makes sense to keep the function body, the guts of the function, the definition of the function, somewhere in a centralized place, so that whenever you invoke the function, you don't have to redefine it. Its definition is already sitting somewhere. So it's nice to separate the definition of the function into a separate file. And that is what motivates the modular organization of the C programs. Typically, programmers provide both an implementation of the function and an interface. So implementation could be a C source code or precompiled object or library file. And interface is the definition prototypes of the function in the header files that tell the compiler what the inputs are and what the outputs of the function are. This is precisely how we have been able to use printf and scanf functions without much sweat, because their prototypes were sitting in stdio.h and their implementations were sitting in the compiled standard input-output C library, against which the code was linked under the hood. So here is an example of how we can try to replicate this sort of library approach, where you separate the declarations and definitions of the functions, or the implementations of the functions, as much as you can. This is, of course, a toy example. In reality, the bodies of the functions would be sitting in a library somewhere. But here we're going to separate them into a file. So here is our C file that we will call hello with header.c, where in addition to the standard input-output header, we now have our own header, say hello.h. And this file, say hello.h, all it does, it provides a declaration of the prototype of our say hello function. The say hello function definition, or the body, is going to be sitting in say hello impl.c. That's where the implementation of the function is. And we're going to include that file after main into our hello with header.c. So what is really happening is that this include keyword will take the contents of say hello impl.c file and put them right here at the time of pre-processing of the C file. And then the function main will be able to call say hello, because the preprocessor will have included the declaration of the prototype of this function at the beginning of this file. So that is how the separation between the declaration and definition of the function can be done. So to repeat, we used include to separate the interface or declaration and the definition or implementation of the function in different files. Notice that there is a difference between including files using the angular brackets and using the quotes. The quotes mean that the C compiler will be looking for these files in the current directory. So as opposed to angular brackets, where the compiler will be looking for the libraries in the dedicated locations for the libraries. This is, of course, a very simplified example, but it does convey the idea of separating the interface and implementation files. Let's take a look at something that is more complex. Let us use functions in order to convert temperatures from Fahrenheit to centigrade, the one that we considered last week. And this example highlights one of the crucial aspects of functions, that is reusability. You can use the same function from multiple places. So you don't have to duplicate the code. It's the same function, you just reuse the code. So this looks like quite a big code. So let's go line by line and take a look at that. So at first we are going to include the standard input-output header, stdio.h, and then we will include conversion.h. This is our own header. That's why we include it in quotes. This conversion.h will be sitting in the same folder or directory as our C file. That's why we use the quotes instead of the angular brackets, and it provides the prototype for our brand new function convert to centigrade. It takes a floating point variable, temperature in Fahrenheit, and returns the value of temperature, also floating point variable, in centigrade. The implementation of the function is sitting in conversion impl.c, the implementation of conversion, which we will, as before, include at the bottom of our C file. So let's take a look line by line what's going on here. First, we're going to declare the high, average, and low temperatures in Fahrenheit, the same for centigrade, and we will also declare the variables that hold the month, day, and year. The first two lines declare temperatures, and they are floating point variables, and then month, day, and year are integers. Then we will also declare and define the input and output files. So we're going to open the input file and the output file. The input file is open for reading, and the output file is open for writing. We're going to skip the header like before. Remember, %s is going to skip the first line of the file that describes the naming convention of the columns. And then we're going to go through every line using the while loop. So while loop will scan a line for the date, including the year, month, and day, and then for the three values of temperature, the high, average, and low temperature in Fahrenheit. It will then continue to do the processing of that line if the fscanf call has succeeded, and if it didn't, it will return an end of file value. So if the value is not end of file, then we're going to process the high temperature by converting it from Fahrenheit to centigrade, and we're going to do the same thing by repeating the call to the Fahrenheit to centigrade conversion 2 more times for converting the average and low temperatures. Finally, once we've converted those temperatures, by reusing the same code of Fahrenheit to centigrade conversion, we're going to write the converted temperatures to the output file. And we're going to go back and read the next line and process it, and so on and so forth, until we're out of data. The fscanf returns the end of file, the loop will no longer continue, and we will close both the output and the input files. Finally, at the very end, you can see we can include the implementation of the Fahrenheit to centigrade conversion, but it could have been included earlier or later, and it doesn't matter because we have already prototyped the function at the very beginning of the file. So compiler, after this include line, knows how to call our awesome temperature conversion function and what it returns. So here is the example output, the first few lines of that output file. You can see that it is writing out the date followed by the 3 temperatures, and as before, you can recognize the temperatures are in centigrade, not Fahrenheit, because they are not too high. You know, they are around 0, which is roughly right for January. There are a few cool things about functions that I wanted to share with you in addition to what we just saw. Namely, that you can call functions as part of the expressions. So for instance, in this example, we're going to first declare a global variable foo and assign 5 to it. And then we're going to declare a function, do it, that returns the value of foo, after which it subtracts 1 from foo. And now in the main function, we can call the doIt function from inside the while loop expression, such that while will only iterate while doIt is non-zero. So the first time we're going to enter this loop, doIt will get a value of 5. That's the value of foo. And the variable foo will then hold the value of 4 after the decrement. So the very first printout will be foo equals to 4. And we're going to keep going until the value of foo inside of doIt is 1. So then while we'll get the value of 1 as a return, value of foo will be decremented to 0, and the final printout will be 0. After which, once we get back to the expression here, the value of foo will be 0, and while expression will be false, therefore we're going to exit out of the loop and out of the main function. I hope that makes sense. It's a little bit confusing because the value of doIt and the value of foo are different because of the quirkiness of the suffix decrement. Namely that the return value is the original value of foo, and but the value of foo itself will be decremented, as you can see here in the printout. Another interesting thing about functions is that a function can call itself a process referred to as recursion. So let's take a look at what that is. So far things are pretty similar, but we now declare a function do it again. And do it again will continue as long as foo is non-zero, and will printf the value of foo that was decremented by 1. And then it will make a call to itself that will do the same over and over again. It will print out a value of foo that was decremented by 1. And in the main function, it makes a call to do it all again. So you can see that the result is identical, but it's accomplished via different means of recursion. Function calling itself, and here again, we're using a different type of decrement. This is a prefix decrement. There are other interesting things when it comes down to functions. If you call a function and give it a variable, the function gets a copy of the variable. So no matter what it does with the variable, the original variable will not be changed, the one that we passed to the function. So it would be nice if functions could modify the variables that we pass them, so that they could do something with its variables and modify them. This is precisely what happens in our call to scanf function. But wait, here, see, we had to include this ampersand signs. So what we actually did, we didn't pass the value of the variable, like day, month, and year. We passed the addresses of these variables to the function. And so although the function as scanf got copies of these variables' addresses, a copy is good, because a copy of an address of the variable allows the function to go to the location where the variable is stored, modify the value of the variable at that location, and that way it will be able to modify the variable that we passed it to by pointer, by reference. So that is the key difference. when we pass the addresses of the day, month, and year variables to scanf, the day, month, and year of the variables that we pass the addresses of to scanf can be changed by scanf. So let us try and make an analogy. Pointer and address in terms of real life. So one way to think of pointers and addresses is the mailbox analogy. So let's say we would like to communicate with each other, and for that we will need two pieces of information. We would need the information content, which is the letter, which contains the content, and we also need an address where to get that letter and retrieve the content, therefore. In C, the letter corresponds to the value of some variable. The mailbox is the location where that variable is sitting, so the memory location that holds the value. And the mailing address is the address of the location, address of the mailbox. So if we know the address of the location, we can go there, pick up the variable, modify it, examine it, read it, put it back. And that's precisely what you can do with a letter. Once you know which mailbox the letter is in, you go to the mailbox, open the letter, modify anything you want, put the letter back. And that is precisely how the pointers work. Of course, the analogy is not perfect. That's because in C you can access the letter contents directly by accessing the variables without going through the address of the variable. But when we access the variables through the addresses, this analogy works pretty well. So let's talk more about addressing. The address of a variable is obtained through the ampersand operator, as we've seen with our scanf, fscanf experience. So for instance, in this address.c example, we are going to define two variables, foo equals to 1 and bar equals to 22. And then we are going to print out the value of foo, and we're going to print out the address of foo. And we will do the same thing for bar. And you can see that these variables were defined one after the other, so their addresses are almost sequential, but not quite. The address of foo is 4 units larger than the address of bar, and 4 bytes is precisely the length of an integer variable. So indeed, these variables are sitting in memory back to back, and that's why the addresses are different by 4 bytes. And of course, the values of the variables are the ones as we expected, the ones that we assigned. So the large number that we saw is that address in the stack of the memory location. Every time you run the same program, it changes. So for instance, if you run it twice, you will see that the addresses are going to be different. But what is going to be the same is the difference between the addresses of foo and bar variables. That difference will always stay constant, equal to the size of the variable, namely 4 bytes. That is precisely the size of an integer, just as we discussed. So what is going to be the type associated with the variable address or with the pointer? So would it work if it was just an integer that told us how many bytes are there between the beginning of memory and the location where the variable is stored? That is basically what the pointer is, but it's a little bit more complicated because there are different types of variables, and they take up different number of bytes, different amount of space. So when you increment the pointer by 1, you would like to jump from one variable to the next, as opposed to from 1 byte to the next. And so a pointer type is a type that is size aware. So pointers to integers, floats, and characters are going to be different. They are going to be aware of the size of the variable that they point to. And when you increment the pointer by 1, they're going to hop over just the right number of bytes to point to the next memory location where the next element of that type will be sitting. So star here implies an object that points to the memory location. So if foo is a pointer, star foo will be the value that's sitting at the location that's pointed to by foo. So how do we use pointers? Here is a simple example. Let's define a variable foo equal to 22, and then we will define a pointer bar that points to the location of foo. Ampersand foo is the address of the location of foo. Now we can access the variable foo in several different ways. We can directly access the variable foo by referring to it by its name, or we can also access it by referring to it by the pointer to that variable. So star bar and foo will be the same exact variable foo, just accessed in different ways. And you can see that bar, the value of the pointer, is some big number that is going to change every time you call the code. However, the value star bar will always be the same as foo because star bar points to the same location. So bar points to the same location as foo, and star bar will be exactly the same value as foo. You can modify the variable through the pointer. So here is an example of how you can do that. It's called pointer.c. We will introduce the variable foo equal to 22, a pointer bar that points to the location of foo, and we're going to print out the value of foo. We will print out the value of pointer to foo, that is bar, and we're going to print out the value star bar, basically the value of foo, the value that is located at the location of foo, that is foo itself. Then we're going to change the value of foo through the pointer bar. So we will say star bar is equal to 333, and after that we expect that the value of foo will change, and that's precisely what we see. We start out with the value of foo of 22. This is a value of bar that doesn't have any physical meaning. It's just happens to be the address of the location where foo is sitting. The value of bar is not surprisingly the same as that of foo. And then after we change star bar, we're going to see that the value of foo will be equal to exactly that value to which we set star bar. So I hope that makes sense. If that's confusing, please post your questions in Slack or ask Lindsay and I during the hackathon and office hours. Let's talk more about pointers and arrays. That is really, really cool, right? Arrays and pointers, it turns out that they are more of the same. They're very, very similar. We have been accessing arrays through indexing so far. So for instance, if we define an array foo of an array size, that is a constant, and we will assign the values of 1, 22, 333, and 444 to its 4 elements, then we can loop over all those elements and we can print out their values. But we can also access the elements of the arrays using pointers. Unlike a single variable, an array is a bunch of variables stacked one after the other. It's essentially a segment of memory. And you do not need to use an ampersand sign in order to obtain the location of the array. The variable foo itself will already be the address of the first element of the array. So in order to obtain the address of the array, all you need to do is to say int star bar is equal to foo, and bar will contain the address of the first element of the array. You could equivalently write this as int star bar is equal to ampersand of foo 0 in brackets. So that would be the address of the very first or 0th element, because in C, all the indexing starts with 0. So the usual C operations apply for pointers. but the pointers are of a weird address type. So if you assign bar equal to foo, then bar plus 2 will refer to the address of an integer that is 2 locations away from the beginning of the foo array. Not 2 bytes away, 2 integers away. That is precisely why we need the addresses to have types, which is specific to the type of variable to which the pointers point. So what are the other operations that you can perform on the pointers? You can evaluate their values and compare them to each other. So if foo is equal to bar, it means that both pointers are pointing to the same memory location. You can increment and decrement, or you can do some sort of compound assignments on the pointers. So for instance here, you can loop while the value at the location pointed to by the foo pointer is not 0, actually positive. You can keep incrementing the address stored in foo until you hit the value that is 0 or negative. So this is a way of sweeping through memory. This is useful, for instance, when you're trying to find the end of a string. That's what you would be doing, because strings in C are 0 terminated. So here is a more complete example where we define the size of the array as 4 elements. Each of these elements is an integer taking up 4 bytes. And this is our main function where we define a pointer that is pointing to the beginning of this array. So star bar will be equal to 1. And then what we're going to do, we're going to loop over bar. We're going to keep incrementing the pointer until it hits the last element of the array. And we're going to be printing those values. And you can see that we're going to loop over all of the variables in this way. So here, bar equal to foo is the first element. Bar plus 1 is, so the 0th element. Bar plus 1 will be the first. Bar plus 2 will be the second. And bar plus 3 will be the third, the last element of the array. And bar plus 4 will be the one element that doesn't exist. It's the element that would be after 444, the last element. That's precisely why the print loop goes over all the elements of the array. Be very careful when dealing with the pointers. It's very easy to mess things up if you, for instance, use a non-initialized pointer and try to read from memory pointed to by that non-initialized pointer, or even worse, try to write to the memory. You can cause crashes, in the worst cases, computer reboots, stalls, hangs, and so on. So that might sound bad, but even worse is if the pointer is pointing somewhere valid. Then what can happen is that you will modify unwittingly other variables that you didn't intend to. And that can happen if you step outside of the defined memory bounds in the pointer. So you get an out of bounds error, as we discussed. Those errors are extremely hard to catch because they can be non-reproducible. So if you run the code multiple times, you can modify the values outside of the array in slightly different ways, because different things can be located beyond the array that you're stepping out. And there are tools in order to catch those variables that I'm going to talk about in later lectures. So let us recap that pointers and functions allow us to pass variables by reference. So if you pass the pointer as an argument to a function, the function receives a copy of that, just like with a regular variable. But now that we've gotten a copy of the address of a variable, we can now go and check out what's hanging in there at that address. And if we want to, we can read the value of the variable at that address or modify the value of the variable at that address. So that basically means that this allows the function to indirectly modify the value at the address. just like we did with scanf. So here is another example that shows how C code can be very compact and make use of the operator precedence. So let us declare our own function that copies a string from source to destination. Both of them are pointers to character, pointers to a string, to the first element of the string array. We're going to define a string called foo, and we're going to define a string called bar of the same size as foo. Size of foo tells us how many elements foo contains. So this is a convenient way of making sure that we create two arrays of the same exact size. Then we're going to make a call to our function that we will check out in a second that copies the string foo into a string bar, and then prints out both strings to ensure that the copy was successful. And upon the end, it returns a value of 0. Until now, we worked with main functions that didn't return anything, but here we've defined a main function that returns a 0. It can be useful if you call a program that it returns a value, because a 0 value typically indicates success and non-zero value indicates a type of error. So 1 would be error number 1, 2 will be error number 2, and there can be a lot of errors as high as ints can go. Here is the guts of our function myStruCopy. As you might have guessed, StruCopy is strucpy is the standard function that's available in C, but we've written our own variant of that. And you can see how compact it can be. You can stop the while loop with a semicolon such that the while loop doesn't have any body, because the expression itself is the body of the loop. So what it does here, let's take a look in more detail. So let's take a look at star src++. The ++ takes precedence over the star, as you can check back into our precedence table. And that means that the star dst++ equal to star src++ will assign the value that's located at the location pointed to by the src pointer to that of the dst pointer. So the first element of dst will be assigned to the first element of src, which is precisely what we wanted. Then after that assignment, the postfix increment will kick in and will update the pointers by 1, pointing to the first element of the string, and then we're going to go to the next and the next iteration of the loop. This while loop will continue while the value pointed to by the src pointer is non-zero, meaning that we are not at the end of the string. Once the end of the string is achieved, its value, the 0 character that's terminating the string, will be copied first, and then while will be checked whether that value is 0. If it finds the value is 0, the loop breaks, and then the function ends. So you see, this is a very compact way of copying one string to another, literally using a single line and postfix increment, as well as the pointers. You don't even need to define any new variables, because all you need here is to play around with the pointer arithmetic. And of course, the output of this function is going to be foo and bar, which are identical in contents. Just as we intended, we wanted to create a copy of foo. So let's take another example. Let's take a look at another example where we can use pointer arguments to modify something from inside of the function. So let us define a function add1 to my int, which accepts a pointer to an integer. Then it goes and finds that value of integer in memory by dereferencing the pointer and adds 1 to it. This is the main function here. We start with the variable bar equal to 22. We're going to print the value of bar and we're going to get 22. We now are going to add the 1 to bar. So after that, when we print it out, it will be 23. And if we make another call and print out the value, we will get 24. So you see that by passing the address of bar to the function now has indirect access to the bar variable through its to the bar variable through its address, right? We pass the address of bar to the function, so it can now find where the variable lives, knock on the door, change the value of bar, and that's how the value of bar is going to be updated here. Note that in this case, we again have to resort to the precedence rules, where plus plus star foo means that plus plus is acting on star foo as a whole, so it is incrementing the value at the location of foo as opposed to the pointer, the foo itself. So let's try and get a better idea of how to work with pointers to modify the information that these pointers point to on a practical and very important example of sorting an array. And the specific algorithm we're going to use for that is the quicksort algorithm, which is much faster than a straightforward algorithm like a bubble sort, where you go over the array and if you find two elements that are out of order, you change the order and then you keep going over and over and over until ultimately the entire array is sorted. Quicksort works much better by breaking down the array into compartments, into subarrays, and sorting each of the subarrays individually. And that allows it to be much faster than the bubble sorting algorithm. So let us re-implement the quicksort algorithm from Kernighan and Ritchie's book on C programming. The idea is to sort the array in increasing order. And the way that this algorithm works is we will first pick an element, which we will pick to be the middle element of the array, and we're going to partition the array such that all the elements that are small in this one will be on the left side, and the ones that are larger will be on the right side. And then we will call that algorithm to sort this smaller subset and separately the larger subset, which then will get automatically sorted, and the entire array will get sorted as a result. So let us first introduce an important helper function that will swap two elements in an array. Not surprisingly, it's called swap, and it takes two pointers, pointer 1 and pointer 2, one to the one element and the other one to the other element that we would like to swap in memory. And the way it's done, you can't just directly swap the two elements. You need to have a third element to hold a temporary value. So that temporary value is int tmp, that is equal to the value at the first pointer's location. And then once we've put that value in the pocket, this temporary pocket, we're going to take pointer 2 and copy the value to pointer 1. And then we will take the value from the pocket and put in pointer 2. So that way we swapped the two values. And with this, now we're ready to implement the qsort routine, which at its core is a bunch of these swaps in such a way that the array eventually gets sorted in the increasing order. So here is the entirety of the algorithm. It looks deceptively simple, but actually it's a little bit complicated. So let's go over it slow, line by line, and then we're going to take a look at an example of how this algorithm gets to sort an array. So the qsort algorithm accepts two pointers, left and right. The left one is the first element to be sorted, and the right one is the last element to be sorted. So everything, including these two elements and in between, will be eventually sorted. We introduce three helper pointers. Pointer to the current element that we're evaluating, PTR. Last is the last element that has been put in the right place. And middle is the one that we will divide the array into two halves, the smaller and the larger half. Then we will get to it. So if the left pointer is greater than the right pointer, then the array is it doesn't make any sense, because the left one is supposed to be less than the right one. So then we will get out of here, not going to change anything. Something is wrong. Then we will introduce this dividing element, which we'll pick to be the middle element between the left and the right element. Then what we're going to do, we will take the middle element and we're going to put it at the beginning of the array. Okay? Then all we need to do in order to sort the rest of the array is to take the smallest elements, small in the left array, and put them all in the left half. And once we've done that, we're going to put the left element back to where it was. So that way, we're going to end up with an array that is divided by this middle element, such that the left part of the array is all smaller than this middle element, and the right part of the array is greater than the middle element. This is accomplished by this algorithm here. And once we, and this is, yes, this is accomplished by this algorithm, and then this last swap is going to put that element back into its place. And after that's done, we now have an array that has been broken down into two halves, the one that's smaller than the middle element, the one that's larger than the middle element. So what is left to do is to call our QSort algorithm and give the left half of the array and the right half of the array as arguments to it. So that's precisely what's done here. So let's actually take a look at how this algorithm works in practice, because looking at specific examples is oftentimes extremely helpful. So let us give this QSort function a pretty short array. Array size is 7 elements, and here are the elements which are kind of in arbitrary order. Clearly the array is not sorted. And we're going to call QSort and give the pointer to the first element of this array, which is array itself, and to the last element of the array, which is array plus the number of elements minus 1. So that will be precisely the pointers to the very first element with index 0 and the very last element with the index array size minus 1. So first, if you remember the algorithm, and you can go back in the slides or you can rewind back, QSort checks that the left pointer is actually to the left of the right pointer. So that is the first check that it performs, and sure enough, in this case, left is smaller than right, or to the left of the right pointer, so we're good. We're passing this first sanity check. Then it assigns the middle of the array to the middle pointer. And this is the array element that divides this array into two halves, the left half and the right half. So now that we have created this division, we are going to put the middle element, 9, into the leftmost compartment and put the 5 in place of the middle element. So we're going to swap these two elements, which is precisely what you see here, the result of the swap. So now the goal of the algorithm is to take the rest of the elements and collect all the elements that are smaller than the middle one, smaller than 9, to the left of these 6 rightmost elements. So 9 is going to be sitting here forever, and then these 6 will be reshuffled such that the smallest ones, the ones that are below 9, smaller than 9, will be collected to the left. So it's kind of you're sifting through the elements and you're letting the smallest one fall through to the bottom of this if you think that you put it vertically. So you're kind of sifting through like the flour, and all the smallest ones, the ones that are smaller than 9, are going to collect to the left. That's literally what the algorithm is doing. So it does it with the help of left and last and PTR pointer. So first what it does is that it is letting the pointer PTR to walk down the array. So it starts at the very first element, that is right after 9. So it needs to walk through all of these elements. And what it does, for every element it checks, is it smaller than 9? Aha, okay, well, if it's smaller than 9, let's swap it with the element that is right after last. So last one is the one that's in its place. So this one is in its place. This one is going to be swapped with the one that's after last, so it will be swapped with itself. Basically, it means that this element is already in its location. Indeed, it is smaller than 9, so it's going to be sitting right here. Then the next step is to increment the last to point to this element, as we will see later, because this element is in its place. And then we're going to increment PTR as well. So that is basically what we're doing. We're incrementing the last, and then we're going to increment the PTR. And then we're going to check, is 32 less than 9? No. So we're going to step forward, and we're going to see, look at that. 5 is less than 9. So that means that we're going to take the next element after the one that was sorted. This is where last used to point. We're going to increment last to point to the element that is out of order. And we're going to swap these two, thereby moving 5 as much to the left as possible without touching the ones that we already put in the right place. And PTR continues its sweep further and further. So that's where the swap happens. So now you see what we've gotten is we've taken -6 and 5, and we've pushed them as much to the left as possible. And the walk continues. So for instance, nothing happens until when PTR hits 13, because 13 is greater than 9. But when it hits -1, then the same algorithm will continue. What it will do is it will increment the last, so it goes from -5 to 32, and it will swap these two elements so that -1 will take the place of 32. And so you see that we have obtained exactly what we wanted, namely take all the elements that were smaller than 9 and place them as much to the left as possible, leaving the elements greater than 9 or equal to 9 in the right part of the array. So in order to complete our algorithm, what we need to do is we need to put 9 back into the middle by swapping -1 and 9. And that's precisely what is happening over here. We have, before the swap, we already have elements that are smaller than 9 sitting in the left side, greater than 9 or equal to 9 in the right side. And as I said, we're going to take this element, put it on the left, and put 9 back where it was, just so that we actually have something that resembles increasing order. Small elements, middle element, and large elements. And then after that, we're going to make another call to qsort to sort these 3 elements on the left, and another call to qsort to sort these elements on the right. And why that works is because we now know that this 9 is in the correct position. The only thing that the sorting subsequent to this state will do is reshuffle things to the left or to the right of 9. There's no way that 13 will ever end up to the left of 9, because 13 is greater than 9, and so are the other elements here. And the same thing applies to the elements to the left. So by sorting on this middle element allows us to then focus on smaller subarrays of the big array. And that is what allows the qsort algorithm to be so efficient. So then, like we said, we're going to apply the sorting such that the left and the right for one of the qsorts call will point to these 2 elements, -1 and 5, the left half of the array, and another call to qsort will work on these 2 elements, the right half of the array. Not exactly half, they don't have to be equal to each other. So I would say left part and right part, because half implies equal division. In fact, it doesn't have to be equal. One the yellow segment could be larger than the purple segment. And it all depends on how many elements that were smaller than the initial pick of the middle element there were. If there were a minority of elements that were smaller than 9, then this left half will be less long than the right half, or the converse. So as a result of this recursive algorithm, we're going to end up with an array that, while started unsorted, will end up being sorted in increasing order. So with that algorithm conquered, using two concepts that we learned. One is the pointers and the other one is the recursion. We are going to return next time to fill in some details that we had to gloss over. We're going to introduce the concept of structures. We will talk more about pointers, and we will circle back and refresh our memory how to use Python and GNUplot for plotting. Thanks so much for your attention. It was a lot of fun, and I hope it was fun for you. And I'm looking forward to seeing you at the next hackathon office hours. See you soon. Bye.